Okay, let's get started. I'm going to have a crack at the first PHYS1001 test for the year. I'm going to do it in a semi-naive way. Obviously I've seen it before, so I know what's in it, but I'm going to pretend that I'm not super duper good, because I'm not. That's easy to pretend. So here it is, and I'm going to go to the back and attach the answer sheet, my blank page for working. Alright. Okay. Let's see if we can go as well as the Dockers went yesterday. Okay, so first question. The coefficient of linear expansion of steel is 11 by 10 to the minus 6. And the coefficient of volume expansion of a certain cooking oil is 5.92 by 10 to the minus 3. Pot's 90% filled with the cooking oil, both at 24. If the pot and oil are both slowly and uniformly heated, the temperature which the oil will start to spill out of the pot is closest to. Okay, so I guess we should do this exactly. We should say, alright, initial volume of the pot. The volume of the pot is going to be, well, the change in the volume of the pot is going to be 3 times the coefficient of linear expansion, 3 times 11 times 10 to the minus 6, because that's linear and volume is always 3 times, times the initial volume of the pot, times the temperature difference, which will be basically T minus 24. We don't need to go to Kelvin for this because it's only concerned with changes in temperature. And the change of volume of the oil is going to be equal to just the volume expansion times the initial volume. Now this is initial times T minus 24. Okay, now that initial volume is 1, this is 0.9, and okay, well, we need the change in volume of oil to be 0.1 litre plus the change in volume of the pot, because the pot's getting bigger, so 0.1 litres change would get us up to the volume of the pot, but then the pot's got bigger too. So this has to equal to 0.1 plus that. Okay, so 0.92 by 10 to the minus 3. Now T minus 24 I might just call X for now, just to times X times 0.9 is equal to 0.1 plus 3 times 11 by 10 to the minus 6 times X, and I guess I've got to rearrange, so I get 0.92 times 0.9, that's that, minus 3 times 11 times 10 to the minus 6 times X is equal to 0.1. Okay, rearranged. So X equals, okay, so it is 0.1 divide brackets, or 0.92 times 10 to the minus 3, 10 to the minus 3, 0.92 exponent minus 3 times 0.9 minus 3 times 1 exponent minus 6, close brackets equals, and I'll get 125. X is 125 and 0.786, and of course, so therefore T is equal to 24 plus X, so add 24 to that and we get 149 point blah blah blah. 150 is the answer. Okay, yeah. Did I enjoy that? No. Could you have made it easier? Yes. If you were smart, you could have looked and said, look, this expansion due to that is going to be a lot smaller than the expansion due to that, and I can just basically ignore it, because you see these answers are all a long way apart. Okay, so you could have just said, look, I just need that to get me from 0.9 to 1 litre, and done that calculation, and you would have got pretty close to 150, and that's the only possible answer. So yes, you could have done it better, but it doesn't matter if you didn't. Now, in this one we have pressure and volume both doubled. So to start with, we have P naught V naught equals N R T naught. Now we're going to double them, so we're going to 2P naught 2V naught equals N R, and obviously it's going to be 4T naught if we still want it to be true. So therefore, in doubling the pressure and the volume, we must have 4 times the temperature. Now the kinetic energy is proportional to the temperature, so half m v squared is proportional to temperature. So therefore, if we multiply the temperature by 4, we just double the velocity, because 2v squared gives you 4v squared. So therefore we're going to double the velocity. So we started at 500, and d we're going to get 1000. No problem. I think most of you got that. Alright, now the hard bit. Some easy, some hard. Let's go through it. So this is one, you've probably got to read it. You're going to feel like you're wasting time, but do it anyway. So, an ideal gas initially in a thermodynamic state I, there, and finally in a state F, there, is taken through one of two possible processes labelled 1 and 2 as shown. So 1 is there, there, and 2 is there, there. The plot shows as dash curves two different isotherms for temperatures T1 and T2. So we can see that state I and state F both are actually at the same temperature, but if you go via state 2 you get to a much hotter temperature there. Alright, and then here's a description of the temperatures. Process 1, an isochoric, which means without changing the volume, cooling, followed by an isobaric, which means without changing the temperature, the pressure rather, expansion. And process 2, an isobaric expansion, followed by an isochoric cooling. Okay, so the first thing we're asked to find is the temperature of T2 of the gas when in state A is closest to what? Okay, so T1 is 300 K, V1 is that, V is that. So one equation I know you guys are always really great at is PV equals nRT. So what we've done here is we've doubled the volume, and therefore we've kept the pressure the same. The volume's doubled, the pressure stayed the same, so the temperature must double. So if we started at 300 Kelvin, we must end up at 600 Kelvin, and I think most of you got that. The work done on the gas during process 1 is closest to. Okay. Well, so let's have a look at that. So process 1. You only do work when the volume changes, and if we go down there, the volume does not change. So the volume only changes here. And how much work will we do? Well, we're going to do work equivalent to that area. In other words, it's going to be Sorry. Something's gone wrong with the recording. Let's hope it comes back. Okay, hopefully that's still going. I don't know what went wrong there. Okay, so if we knew what this pressure was here, if we knew what that pressure was, we could multiply by the change in volume, which we do know, and figure out how much work. So, well, we probably should know what the pressure is, because we know the temperature here is T equals 300, and we know the final volume is twice the initial, so we should be able to work out the pressure. So let's do that. Okay, so PF, I'll say, times VF equals N equals PI times VI, because they're the same temperature. And from PV equals nRT, we can write that PI equals nRT over VI equals, so that's 1 mole times 8.315, which is R, times TI, which is 300, divided by VI, which is 1. So we can say 8.315. I made this harder than I needed to. So roughly 2495 pascals. Okay, I have made it harder than I needed to, because if we now go here, PF times twice the volume is equal to PI times the original volume, which is half. So we've doubled the volume, therefore we must halve the pressure. So the PF is equal to 1 divided by 2. 1247.50. Okay, so the work done by the gas is the pressure, 1247.50, times the change in volume, which is just the final volume minus initial, which is 1. So we get, roughly speaking, 1250 joules. Okay, now this is the work done by the gas, because it expanded, so the work done on the gas gets a negative sign, and C is our answer. Oh boy, yes, it really wasn't fun. Now, next question. The change in internal energy of the gas during process 1 is closest to? Well, we have a look at the picture, and we have gone on an isotherm. Okay, yeah, we went by a funny route, but we started and finished at the same temperature, and the internal energy of an ideal gas only depends on its temperature. Therefore, the change in internal energy is zilch, 0 and none. I'm not even going to think about if you were to try and work it out by getting the change of internal energy there and the change of internal energy there. That would be very hard, so we don't have to do it. Okay. What about the heat added to the gas during process 2 is closest to? Alright, I think this is getting harder. So process 2, let's look what happens. We go along here, and we definitely have to add heat here, because we are increasing the volume while keeping the pressure the same, and so we must be heating it up and adding heat. And then from here we are taking away heat, because here we are, we're reducing the pressure while keeping the volume the same, so we're basically cooling it down. So I think, sadly, we just have to work out the heat in both cases. Ooh, Am I happy? No. I'll try and do it, and we'll see if I get it. Right. Heat added to the gas. Right. So, what's the work done in 2, the first bit of 2? Well, it's equal to the initial pressure, which we already worked out is 2,500 Pascal. So it's equal to 2,500 Pascal times the change in volume, which is 1. So it's equal to 2.5 kilojoules. That's the amount of work that's done by the gas in process 1. Now, what's the change in internal energy of the gas? Sorry, in process 2. What's the change in internal energy in the gas? Let's go back to here. So we've gone here. You see we've heated up. We've heated up by 300 Kelvin. Okay. So I'm going to look at my formula sheet because sometimes I get like I need a formula sheet, and U, internal energy of a gas, is 3/2 nRT. Okay, good. That's what I need to know. So the change in internal energy is equal to 3/2 N. How many moles was it? I think it was 1 mole. 1 times 8.315 times the change in temperature. Now we've already worked out before that we went from 300 to 600, so the change in temperature is 300, and this is equal to, so let's do this calculation. 3 divide 2 equals times 8.315 equals times 300 equals, and I get 3742 joules. Okay, that's the change in internal energy. Alright, so looking at these two, so on our first leg where we went across, we've increased it by that much, we've done that much work, so we need to add these two together. So I'm just going to go roughly, that's 3.75 kilojoules plus 2.5 kilojoules, that's going to be 6.25 kilojoules of heat has been added going on the cross one. Now we've got to go down like that. Now this is going down from there to there. It's being done at constant volume, and so the amount of heat that is going out of the system as it cools is just going to be NCV NCV delta T. Okay, formula sheet to check. Q equals NCV delta T. Okay, and CV for a monatomic ideal gas is 3/2 R. So therefore the Q in this case is minus 1 number of moles times 3/2 R times 300 minus 1.5 times 8.315 times 300 equals minus 3741. Oh look, the amount of heat we had to add and the amount of heat we lost there are the same, so we're just left with that. Okay, so 6.25 minus 3.75 should leave us with 2.5 kilojoules. Okay, so we go for D. Oh, that was hard. Okay. Difficult. Okay. And the change of entropy of the gas during process 2 is closest to. Okay, so change of entropy going from there to there to there. Now, the trick, if you like, with change of entropy is a state variable. So entropy basically depends only on the initial change in entropy, only on the initial and final points, not on how you got there. So let's choose a path. Let's choose that path. Okay, that is a nice easy path. The temperature doesn't change. Okay, the temperature doesn't change, so therefore all we need to do is find the amount of heat that we lose by following that path, I suppose. Now, I go to my formulas because, oh look, here's the amount of work that I do if I follow an isothermal path, right? Why is that useful? It's useful for one particular thing, in that because the internal energy change isn't changing, any work that I do, the heat added is going to be the opposite of it. Well, it's going to match the heat added because the internal energy is not changing, so the work the gas done. So this is like, looks pretty good to me. So I'm going to say that work equals heat equals formula nRT log final over initial nRT logarithm VF over VI, which in our case is 1 times 8.315 times the temperature, which is 300 the whole time, times log of twice log of 2. Okay, so calculator, 1 times 8.315 times 300 times natural log of 2 is 1729.05 blah blah blah. So that's the work. But entropy is Q over T, change in heat over T. So therefore I need to divide this by 300. So divide by 300 and I get 5.76. Okay, and there it is. Beautiful. Okay. So Darren there is testing your ability to apply some formulas and your recognition that entropy is a state variable. It doesn't matter how you get from one to the other. So we've done that. This is hard work. Okay. Let's have a look at this one. Okay. So I'm reading this and I'm thinking, right, 1 mole, monatomic ideal gas, CV 3/2 R, initial temperature 53, and then adiabatically expands to double its volume. The work done during this expansion is closest to. I think it was one of the practice problems in one of the assignments that was like this. It's adiabatic, which means no heat is added. So therefore, any work done corresponds to the change in the internal energy of the gas. Alright? Because there's no heat transfer. So, maybe I'm going to look at the adiabatic formulas, and I could use that, but I'm actually going to use this. TV to the gamma minus 1 is constant. Okay. So temperature times volume to the gamma minus 1 is constant. Okay. So that says our initial temperature times our initial volume to the gamma minus 1 is equal to our final temperature times our final volume to the gamma minus 1. Rearranging, I'm going to put TF, I'm going to write TF over TI. TF over TI is equal to VI to the gamma minus 1 over VF. to the gamma minus 1. And this, but Vf, we remember, is double Vi. So therefore this is Vi to the gamma minus 1 over 2Vi to the gamma minus 1, which is it's just 1 over 2 to the gamma minus 1. Without everything else cancels out. So calculator, 1 divide 2 raised to the power. Now gamma, it's an ideal monatomic gas, so it's 5/3. 5 divide 3 minus 1 equals, okay, 0.6299, 0.63. Okay, that is, the final temperature is equal to 0.63 times the initial temperature. Now, the initial temperature is 53. 53 plus 273 equals 326 times 0.63 gives us final temperature of 205.38. Don't need that. So our change in temperature then we need internal energy. Internal energy equals 3/2 nRT for a monatomic ideal gas. So our change in internal energy is equal to 3/2 nR delta T, which is 3/2 times 8.315 times now the change in temperature. We've gone from 273 plus 53, so we're going to times this by -1 and then plus that to 53 plus 273 equals 120 times 120.6, and so the change in internal energy is that times 8.315 times 3 divided 2 equals, and I get 1504 joules. Okay, so as I said right at the start, the work done on the gas is equal to the change in its internal energy because there's no heat flow either way. So we're looking for an answer that's 1500 joules, that one, and it's an expansion, so clearly the gas does work, so that's why the negative sign. So 1504 joules. Well, that was hard. Now here's the next one. I'm not sure if it was accidental or deliberate, but the formula was left out. So this is a case of a sphere that is getting rid of heat at a rate of 1.2 kilowatts, and we need to know what temperature it is. So it's blackbody radiation. So the power is given by the emissivity times the sigma constant times the area times t to the 4th. Okay, I remember that formula. I don't know. Anyway, so it's pretty straightforward. We need 1200 is equal to the emissivity is 1. We need sigma, which, look it up on the sheet, it's 5.67 by 10 to the minus 8. 5.67 by 10 to the minus 8 times the area. Area of a sphere is 4 pi r squared. That's times 4 times pi times 0.15. 15 centimeters is 0.15 squared times t to the 4th. Alright, so rearranging, we get t to the 4th equals, and I'll do the calculation. So 1200 divide 5.67 exponent minus 8 divide 4 divide pi, where the hell's pi, divide 0.15 x squared equals, and I get 7.48 by 10 to the 10th, and I want to take the square root of that and take the square root of it again, and so T equals 523, but that's Kelvin of course, so therefore T equals, take away 273 equals, oh, not divide to, times 273 equals minus 273 equals 250. 250 degrees C. Beautiful. Okay. Nearly there. Another calculational question. Oh, it's so hard. Let's do it. A 1 kilogram mass of water initially at 15 degrees Celsius is to be cooled down in an insulated container by adding 52 grams of ice initially at minus 10. Assume the container is completely sealed and is a perfect insulator so that ice and water form an isolated system. Once equilibrium is established, all the ice is melted. Which of the following is closest to the final temperature of the water? Okay, so basically you want the heat that is gained by the ice to be equal to the heat that is lost by the water. So the heat that's gained by the ice is 0.052. It's 52 grams per ice. And it's going to warm by 10 degrees to get to 0. So that's times 2100 times 10. Then, once it's got to 0, that 0.052 grams of ice is going to need this amount of heat per kilogram. So we times it by 334 by 10 cubed. And then, after it's done that, it's going to be heating up till it reaches the temperature T, the final temperature, which is going to be, so 0.052 times 4190, specific heat of water, times T, the difference from 0 to the final temperature. And that must equal to 1 kilogram times 4190 times the change in temperature of that, which must be 15 minus T. Okay, it's exhausting, and can we do it? Well, I get these two bits there. I get 18,460 plus 217.88 T equals 4190 62,850 minus 4190 T. So therefore I get, add that to there, so 4190 plus 217.88 equals 4407.88 T equals 62,850 minus 60 equals 4390. Therefore divide, therefore T equals, we just divide 10.07 degrees Celsius. So I go for D. It's painfully hard, isn't it? Okay, now here is the first great question that says, consider the entire contents of the container as a single system, a system which undergoes a thermodynamic process starting as ice and water and ending up as water only. For this single system undergoing this thermodynamic process, let the change of entropy and internal energy be denoted by delta S and delta U. Which of the following statements is true? Okay, first of all, it's an isolated system, perfect insulator, so therefore energy can flow from the ice to the water or vice versa, but no overall energy is gained or lost by the system. So therefore that is wrong and that is wrong. Okay, so now we have these three, and these give us three different options for the entropy. This one says the entropy got less, this one says the entropy stayed the same, and this one says it got bigger. And this is an irreversible change. The ice melts. Okay, it's an irreversible change. The entropy increased, so it's this one. Okay, people are tempted to believe that entropy is conserved, right? Entropy is not conserved. Okay, there are times when the entropy doesn't change. This is not one of them. This is the answer, E. And now on to the easiest question of the whole paper. Anyone can just see, just look at it and you go, oh, the answer's D, and you're done. Okay, well, okay, I'm kidding. This was the hardest question on the whole paper. And it's the hardest question because it's tricky. There's no easy way to think about this, okay? Or there are many wrong ways to think about it. The first thing you must understand, and I'm not going to explain it fully here, is that if you're exerting a force F on one end of a string, that means the tension throughout the string is equal to that value. Okay? This is because the string is massless. Okay? The string, we always say, you know, a massless cord or a light cord. It means that the tension is the same throughout. Because if it wasn't, then you would have a force acting on something of zero mass and you would get an infinite acceleration. Alright? So the fact that you don't get an infinite acceleration suggests that the tension is the same, or very, very nearly the same, throughout the cord. What does it mean that the tension's the same? What it means that the tension's the same is that if we cut a little bit of cord here and we said, right, how much force do we need to hold this bit up? And the answer is F. Okay? That's the force we need to exert at that point to counteract whatever is happening on the rest of it. And similarly on this end, we'd have to exert a force F in the other direction. So any little bit that you cut and you put a little man in between holding the two bits together, he has to exert a force F on either end. If he doesn't, the cord will accelerate. Now, the fact is this cord is accelerating, but it still doesn't matter, because with zero mass, it still means that the tension is the same throughout. So when I looked at this, I thought, this is so difficult. I thought, look at the cord going round here, right? Going round there. And at every point, it's going to be exerting a small force like this. It's frictionless, so the force must be at right angles. But you can see that all the horizontal components here and here would cancel out, and you'd just be left with one vertical component acting up. And I thought, I'm going to have to do an integral to find out the sum of all these components, and no, it can't be that difficult. And the answer is, it isn't that difficult. It all depends on what you consider to be the thing that the forces are being applied to. Let me draw a box around this thing, right? Here we are. I've drawn a box around it. Okay? Now, this part here has no mass. This has mass m. So the total gravitational force in our box is, let me draw it here, mg. Right. Our box here has got two cords attached to it, each of them exerting a force F up, and we'll draw those there, and we know how big they are. They're also mg. That's the force acting up. Two lots of those. So therefore the net force on our box is 2mg minus mg equals mg. So our box has mass m, it's got a force on it of mg, so its acceleration is F over m, which is equal to g. Okay, I hope I was convincing. Yeah. Now, there's always a gift question, and this is the gift question. We've got a piano suspended on a rope is being raised vertically at a constant speed of 20 centimeters a second, ignoring the mass of the rope. Well, if it's traveling at constant speed straight up, alright, then the force acting on it, the sum of all the forces acting on it are zero. Okay? Because it's not accelerating. So that all the forces add up to zero. We know the force of gravity equals mg, and that's 400 times 9.8 equals 3920 newtons. So therefore, if the sum of the forces is going to be zero, then the tension in the rope must be that as well, in order to exactly cancel out gravity, give us zero net force, so that there is no acceleration happening. Okay, this next one. Adele throws a stone from the narrowest bridge with a speed of 50 kilometers an hour. The stone is released 1.2 meters above the surface of the bridge. Ignoring air resistance, the stone will hit the water below with the greatest speed if, and lots of different options here. Okay. If you look at the first one, if it's thrown straight up, it'll go up and it'll come down. And when it reaches Adele's hand again, it'll be going at exactly the same speed as it was on the way up. In other words, it'll be exactly the same as if it was thrown straight down with that speed. So the first two are going to give us the same answer. Now, as a general thing, it'll be the same too, because this is where you use conservation of energy. You know that the kinetic energy plus the potential energy is going to be the same at the instant it leaves her hand, at the instant it hits the water. Okay? So, but from the instant it leaves her hand, the change in potential energy is just going to be equal to mgh, where h is the height from where it left her hand to the water. So it leaves her hand with a certain kinetic energy, which is the same for all of these. It gains the same amount of potential energy for all of these, because in all cases it finishes the same distance h below where it started. So therefore, at the instant it hits the water, it now has no potential energy, because we take the water surface to be the zero for potential energy. It's all kinetic energy, and it's the same in all cases, because in every single case it started with the same kinetic energy, it gained the same amount of potential energy was turned into kinetic energy, so it'll be the same. Right. And the last one, which is actually hard, and so it's another difficult question. I'll do it. Okay. Drawing a picture. It's unavoidable. Okay. Alright. So, our mass slides down a slope. It makes an angle of 45 degrees. Okay, we'll make that 45 degrees. 45 degrees. It gains 80 joules of kinetic energy while losing 100 joules of gravitational potential energy. That means that the work done by friction accounts for the difference. 100 minus 80 is 20 joules is the work done by friction. Okay? That means that the force of friction times the distance it travelled down the slope is equal to 20 joules. Right? So, we started up the top. We'll just say it's a height h. And because this is 45 degrees, then this will be h as well. And then this here will be the square root of h squared plus h squared. So therefore the distance here, that distance d squared equals h squared plus h squared. Therefore d is equal to the square root of 2 times h. Okay. So now we've got to find the frictional force. Well, the force of friction is equal to nu times the normal force, where that's the coefficient of kinetic friction because it's sliding. And what's the normal force? Well, it's the component of mg that is in that direction. So if we go there, so we get equals mu equals normal force is mg times cos 45 degrees, which is equal to mg over root 2. So, see, I've run out of energy now. We need mu times mg over the square root of 2 times d, which is the square root of 2 times h, must be equal to mgh. Now, not mgh. So this must be equal. This is the frictional force. This is the frictional energy lost. It must be equal to, it's 20% of the total gravitational energy lost. So the frictional energy lost is 20% of the gravitational potential energy lost. Mg cancels out, h cancels out, root 2's cancel out, and we get mu equals 0.2. Okay. Alright, that is a messy problem. If I was doing it in the test myself, I would have used the blank paper to do that problem. And yeah, so 0.2, and we're done. So difficult test, average mark just under a pass, 7.4. Don't worry, I'm sure the second test is going to be easier.